This is part 2 of the video notes for Objective 3D, Graphing Rational Functions. And in this objective, we're going to take a look at functions that cannot be graphed as a simple transformation of the parent function. For example, you can see in this that we have a trinomial in the denominator, which doesn't indicate a left or a right transformation, and we have input variables in both the numerator and the denominator. So for each example, you'll see in the notes there are a series of steps that we need to go through to find all of the key information. And there is a lot of key information in a rational function. In order to find this, we need to start with step 1, which is always to factor the numerator and denominator. Now the numerator doesn't need to be factored, it's already a binomial, but the denominator can be rewritten as x minus 4 and x plus 1. Each of the key features are very similar to when we were just transforming, except after vertical asymptote and horizontal asymptote, you want to attempt to find the x-intercept, the y-intercept, and then any other additional points that we need in order to sketch the graph. Starting with the vertical asymptote, we want to take a look at what makes the denominator 0, because the denominator being 0 causes a domain error, and the vertical asymptotes represent inconsistencies in the domain. They're non-existent, they cause a domain error. So the first vertical asymptote is x equals 4, and the second vertical asymptote is x equals negative 1. The horizontal asymptote is oftentimes the trickiest to decide because there are 3 possible cases that we need to practice in the video notes. The first case is the one in this example, where the degree of the numerator is less than the degree of the denominator. So as you can see, my numerator is x to the first power, and my denominator is x squared. So that means the degree in the numerator is less than the degree in the denominator. And that gives me a horizontal asymptote of y equals 0. This is true for any time where the degree in the numerator is less than the degree in the denominator. And it's also the most common type of horizontal asymptote you'll run across. The next thing doesn't always happen, in fact it commonly doesn't happen, but x-intercepts occur when the numerator can equal 0. If you have an x in the numerator, you possibly have x-intercepts. So in this example, the 0 of the numerator is 1, because 1 minus 1 equals 0. Y-intercepts we get by plugging in 0 to the equation, so we'll have 0 minus 1 in the numerator, and we'll have 0 minus 4 in the denominator, which gives us a y-intercept of 1/4. With these 4 pieces of information, we have enough to start a sketch. So we need to graph our vertical asymptotes at negative 1 and positive 4. Our horizontal asymptote is just the x-axis, so we tend not to graph it or put a dotted line across it. But we also have an x-intercept at 1 and a y-intercept at positive 1/4. Now this gives me a pretty good idea. You can see that this is decreasing. It gives me a pretty good idea that the inner portion of this graph will look like a cubic. But it doesn't give me any idea of what's happening on the left and the right-hand side. And that's where test points come into play. Anytime you don't have a point in a region, so we don't have a point over here, you need to test it. We're going to plug in negative 2 to test the left-hand side, and we're going to plug in positive 5 to test the right-hand side. You can plug these numbers into either version of your rational equation. I prefer to use the factored form. So for f of negative 2, I get negative 2 minus 1 over negative 2 minus 4 and negative 2 plus 1. And I just want to see if this is going to be more than my horizontal asymptote of 0 or less than my horizontal asymptote of 0. So I've got a negative 3, a negative 6, and a negative 1. And 3 negatives are going to keep my graph negative. So I'm going to graph it down here. For x equals 5, I need to find f of 5, which is 5 minus 1 over 5 minus 4 and 5 plus 1. And so we've got a positive a positive, and a positive, which leads me to believe that this section of the graph is positive. And that actually concludes graphing a rational function. It doesn't conclude our notes. We're going to go through multiple examples. But this is the full 6-step process, and this is what we're looking for each time we graph. When you're done trying a graph by hand, you should plug it into your graphing calculator and just check to see if it worked. There's going to be some inaccuracies when you're learning to graph these, so continuously check until you start to get each graph correct by hand. For our next example, we're going to add some new features. And the big one is that we're going to take a look at the second case for horizontal asymptotes when the degree in the numerator is equal to the degree in the denominator. So for this example, we have f of x equals 2x squared minus x minus 3 over x squared minus 9. I'm going to draw the graph, and while I do that, try to get a head start on factoring the numerator and factoring the denominator, because that numerator is factorable. The first step of graphing any rational function is to factor. And so we are looking for numbers that multiply to be -6 and add to be -1. And what we get is this. The denominator is x plus 3 and x minus 3. And now we have a lot of information we can use to find all of our key features. Starting with the vertical asymptote, when does the denominator equal 0? And that's at -3 and +3. Next up, we have our horizontal asymptote, and this is our second case where the degree in the numerator is equal to the degree in the denominator. So the asymptote is the ratio of the leading coefficient, or in this example, the asymptote is y equals 2 over 1. X-intercepts occur when the numerator equals 0, so if there are x's in the numerator, you likely have x-intercepts. And those x-intercepts are what make those factors 0. So this one is +3/2, and this one is -2. And this is not how we write it. We write it as an ordered pair. 3/2, 0, and -2, 0. The last feature is the y-intercept, which we get from plugging in 0. So we have 0 minus 0 minus 3. And we have 0 minus 9, which simplifies to be 1/3. Just like the last time, we're going to graph our two vertical asymptotes. This time, we need to graph our horizontal asymptote through 2. We have an x-intercept at 3/2, which is 1.5. We also have an x-intercept at -2. And we have a y-intercept at 1/3. Knowing that I need to graph a continuous function, it leads me to believe that this function is going to look like this in the center. But if I wasn't sure, I could always pick test points at 2 or 1 or -1 to be sure. That leaves me with two unknown regions. I don't know what's happening to the left of -3, and I don't know what's happening to the right of +3. So for my test points, I'm going to find f of -4 and f of +4. I've got 2 times 4 minus 3, 2 times -4, -4 plus 2, and -4 plus 3, and -4 minus 3. What's the overall result? Is it more than 2 or is it less than 2? So here I've got -11 times -2. In the denominator, I've got -1 times -7, which leaves me with 22 over 7, which is more than 3, because 7 goes into 22 3 times. So that tells me that it is above my horizontal asymptote. Checking f of positive 4, I'm probably going to get a similar result. I have 2 times 4 minus 3, 4 plus 2, positive 4 plus 3, and positive 4 minus 3. That gives me 2 times 4, 5 times 6 over 7 times 1, or 30 over 7, which is also more than 2. And that is the hand-drawn sketch of the rational function for example 6. Let's try another example that introduces another new feature to our rational function repertoire. In this example, we have f of x equals x squared minus 1 over x cubed plus 4x squared plus 3x. As before, try to get a head start on the factoring of this expression while I reset my graph. In the numerator, we have x plus 1 and x minus 1. And in the denominator, we can take out a common x. And then we're looking for numbers that multiply to be 3 and add to be 4, which is 1 and 3. So the new feature in this graph is a hole. And that hole occurs where the vertical asymptote used to be. X equals negative 1 should be a vertical dashed line, but instead of being a boundary, it eliminates and just becomes one single discontinuity in the graph. Let's go through the rest of the key features. My vertical asymptotes are x equals 0 and x equals negative 3. My horizontal asymptote is the comparison of the leading terms. You can see my numerator is less than my denominator, so my horizontal asymptote is defaulted to 0 or the x-axis. My x-intercepts only occur if the numerator can be 0, which it can at 1. And my y-intercept occurs when I plug in 0, but as you can see here, if I plug in 0, I'm going to get a domain error from the denominator, which means that there is no y-intercept. Now, how do I find the hole? The hole is an error in the domain, so we can't plug in 0. We can't plug in negative 1. We can't plug in negative 1. But if we eliminate this, we can plug in negative 1 to the remaining terms to find our hole. And so the hole becomes negative 1, comma 1. Let's sketch the graph of this function to decide what additional test points we need. We have a vertical asymptote at the y-axis and at negative 3. We have a horizontal asymptote at the x-axis. We have an x-intercept at 1, and we don't have a y-intercept, but we do have a hole at negative 1, comma 1. So none of this is very conclusive. I'm going to need to use test points to decide what the graph is going to look like. So the first point I'm going to test is going to be over here at negative 4. And I have a vertical here. So I'd like to test another point over here, maybe f of 2, and see if I can get a good idea of what the graph looks like. Now there's a chance I need more test points than this, so these are just going to be what I start with. When plugging them in, I want to plug it into the fully simplified version. So I'm going to do negative 4 minus 1 over negative 4 times negative 4 plus 3. And that's a negative over a negative times a negative, which is a negative, and tells me that this portion of the graph is down here. Over on this side, I want to try 2. 2 minus 1 over 2, 2 plus 3 is a positive, which tells me that it should be up here, but then that wouldn't allow me to cross through this point. So let's get a better idea. This is 2 comma 1/10, which is tiny and makes me think that the function should look like this. We're going to try one more test point. We're going to test f of 0.5. So if we plug in 0.5, we have 0.5 minus 1 over 0.5 times 0.5 plus 3. This is a negative divided by a positive, which is a negative, and that is giving me the sense that the graph looks like this. The last area I need to graph, I already have a point. I know that this is positive, so I'm just going to fill in the rest of the graph as a parabola. Go ahead and check this one in your calculator while I reset my whiteboard for the next example. All right, let's repeat for example 8, which appears to be simpler, although there is a negative, which tells me it's going to flip. We have 1 over x squared minus 2x minus 8. While I set up a graph, you factor. Your factors should have given you negative 1 over x minus 4, x plus 2, and we are ready to analyze this rational function. Starting with the vertical asymptotes at x equals 4 and x equals negative 2. The next thing we need to look for is the horizontal asymptote, and because the degree in the numerator is less than the degree in the denominator, my horizontal asymptote is y equals 0. There are no holes because no factors canceled from the numerator to the denominator. And there's also no x-intercept because there's nothing in the numerator that could make this function 0. The last feature is the y-intercept. So I would like to plug in 0. I'm going to get negative 1 over negative 8 or positive 1/8. That's enough information to start my picture, with an asymptote at 4, negative 2, the x-axis is my horizontal asymptote, and I have a point here at 1/8. So I have the feeling the middle portion will look like this, but I'm not going to draw the middle portion until I understand the end behavior, which means I'm going to test points at negative 3 and at positive 5. Plugging in negative 3 gets me negative 1 over negative 3 minus 4, and negative 3 plus 2. That's a negative, that's a negative, that's a negative, and the overall result is negative. When I plug in 5, I get negative 1 over 5 minus 4, and 5 plus 2. That's a negative. That's a positive, and that's a positive, so the overall result is negative. And then the middle portion being positive makes sense because, for the most part, you're not going to have two sides of the function butting up the way that 1 over x squared does. Check this graph with your calculator. This concludes part 2 of the video notes.